So, hello. Let me see where I can stand to see the screen. This is probably good. So hopefully I've drawn you in with my title here, and you're wondering, what do you mean without ERLANG'S tracing tools? Like, how are you going to trace ERLANG without tracing tools? But first I want to talk a little bit about observability. You may have heard of the 3 pillars of observability. I like to think of them not as pillars, but as aspects of observing your system. So like if you think about this cube here, you have 3 different dimensions that you can look into your system from. And the more of those dimensions you look into, like the more information you're going to get. Also, another interesting thing here is that you'll notice that each of the surfaces has one dimension in common with one of the other surfaces, and then the other one's orthogonal. So we'll talk about what that means. So starting off with logs, your logs tell a story about what your system's doing in pretty fine detail. Hopefully you have structured data in your logs, so it's like facts that have some kind of machine parsable format to them. And usually you're going to collect those and index them into some kind of search engine so that you can find them later. Here's some example logs from Phoenix and Ecto. Not particularly structured, but kind of structured. We could reimagine those as being more structured as JSON. It might look something like that. But the idea here is that your logs are useful for long-term forensics, so you could look back at a certain time in a search engine or with some system. And then also sometimes they're used to transport metrics, just because it's a common format that we can process these text streams and pull metrics into some other database. Speaking of metrics, your metrics also tell a different story about your app. Usually they're aggregated in time and have some kind of a tag or a name associated with them so that you can figure out at some certain point in time what was the system doing in general, not in a particular request. And then wrapping up with the last aspect here is traces that tell yet another story about your application, but they are about particular requests, what the particular request was doing. But like metrics, they have tags, and like logs, they have structured data. And then usually, well, always, your distributed traces are what happened in a particular request, but across multiple services, as opposed to just logs from one particular server. Kind of different than logs and metrics, your traces are usually sampled. So you'll decide, as you're collecting traces, you might drop some of them at the beginning of the pipeline or at the end of the pipeline, depending on what kind of data you're getting. And then you might also retain them for a certain amount of time, like you would with logs. So let's talk a little bit about the BEAM tracing tools that we're not using. Just if you're not familiar with them, ERLANG has built-in functions for turning on tracing and configuring what trace patterns you want to collect. The way that basically works is that if you have an interactive process, you can make these built-in function calls into the BEAM, and it'll set up this special tracer process, which there can only be one of per BEAM, and it'll configure the trace patterns there. And then as you make function calls, that trace process is kind of magically told that those function calls occurred, and it filters out the ones that you've asked for and sends them to your interactive process. The big reason that we don't use these for continuous tracing that's always on in production is that if you need to go in and troubleshoot something using these tools, that trace process is already going to be used up, and there's no way for you to use it interactively. Or if you did, you'd just be bombarded with everything that the normal tracing's collecting. There's also, Freddy Bear has the recon trace library that adds some conveniences on top of those built-in functions. In practice, if I'm using tracing, ERLANG tracing, this is usually how I'm using it. So I didn't mention that this tracing is prod safe. It's not going to crash your BEAM unless you tell it to trace everything, which is probably a bad idea because your console will also be full of trace logs. It's designed for interactive use, and like I mentioned, only one per BEAM and only on the local BEAM tracing. So you'd have to do some fancy magic to collect traces across multiple instances. Okay, so let's talk a little bit about distributed tracing theory, how it's different than the ERLANG tracing we just talked about. It all starts with Google's Dapper paper from 2010, so really not that long ago. But that's where a lot of this research was originally done. If you're the type that likes to read papers, go check that one out. It all starts with the span. So you may have heard of tracing spans, which have a name and a start time and an end time. So it's like representing this span in time between the start and the end. And a name is just a description of what was going on during that time. Spans also have parents, so you can have this graph of spans that represent the call stack. So the Phoenix endpoint calls the Phoenix router, and that calls the controller, and that does some ecto queries. And then the router also renders the view. Actually, that isn't true. View is under controller, sorry. And then you might have like a JSON call to encode some JSON. But then each span also knows what its trace ID is, so that they're all associated with this overall trace. Normally, there's one root span that doesn't have a parent, but I don't think that's necessarily required if you had some weird case. We can also represent concurrency in these spans. So both of those HTTP GET calls are children of the Phoenix controller span in this case. So the gap in between them just represents that they're happening in parallel as opposed to one being called by the other. And then we can see that after those two HTTP calls get made, we handle both of the responses and make some database query and then et cetera, do other things. Where it gets really interesting, though, is that these different color-coded boxes represent different services that are being called by those HTTP calls. So we get visibility into not just what my application is doing, but some other service that maybe I control or maybe I don't, or some other team controls. But we can trace into what they're doing using the same tooling and conventions. So in this case, we have a green Phoenix server and a red Rails server getting called by the top-level yellow server. And if we look back in the full context of what the yellow server 1 was doing, we can also see color-coded what the other services were doing all in context. It adds a lot of visibility. The way that this works is that we need to propagate the context into these child downstream services. And the way that we do that is pass in the trace ID and the span ID of the trace that's calling into the other service. And until very recently, this has just been vendor-specific, however you want to do it kind of thing. But the W3C has been working on this context propagation standard, which is great because it allows you to interoperate with different vendors more easily. When we pass this trace context into the downstream services, we don't necessarily know or care what they're doing. We pass in the headers for them to use, but they don't, for example, return a trace payload back to us. They just return the regular HTTP payload that we're interested in. If we look into each of those services, they don't know what the upstream service did. All they know is that they get this parent span and trace information, and then they set up their own trace that has the same ID as the parent trace, and they know about the parent span's ID, but they don't know anything else usually about the parent span. And then each of them sends up their piece of the puzzle. So they say, hey, for this trace, I have these spans that I want to submit up. Each server has its own piece. And then the trace collector thinks about how to piece these pieces back together. So then you get the full trace at the collector end. The collector is also responsible for deciding which traces get kept into your database so that you can search for them later. We might do head sampling, which means we decide at the beginning of the trace whether we're going to keep it or not. And in this case, you can see that the trace is much simpler because we know we're not going to keep it. We might exclude some tracing data just because it saves performance or whatever. We can also do tail sampling, where if we decide at the head of the trace that we're going to trace it, but then at the end of the trace, we decide that we don't want to keep all of them because that would be expensive or it would crash our collector system or whatever if we tried to keep all of them. You might pick them based on whether they have an error in them, whether they have like a long latency span somewhere in an interesting place, whatever, on the tail sampling end. So what kind of observability superpowers does this give us when we deploy this kind of technology? One of the obvious things is that we get these single request flame graphs, which is different than the aggregated metrics that you might be used to using. So this is an example from the Spandex example project that I put together to demonstrate how to use the Spandex library. And the visualization here is provided by Datadog APM. So you can see that we have a plug gateway service, which is just a plug router-based application that acts as a front end for a Phoenix backend service that uses an ecto database. So you can kind of see in real life that there's this color-coded sequence of events that happens during a request. I want to point out that this is different than a CPU profiling flame graph. So they have the same name, but they're actually kind of a different thing, because a CPU profiling flame graph that you might get out of eFlame, for example, is it's kind of sampling the CPU and getting a stack trace over and over and over again, and then averaging together all the stack traces to make the width of the stack line up with how many times that was seen during profiling. So this is useful for figuring out what your system is doing if you don't really have any kind of instrumentation in there. But obviously it's inefficient because it's going to trace every call. You can't just do that all the time. That would be like if you have a slow process that you want to try to run in a benchmarking environment, you might use this to figure out what it's doing. The other superpower I want to talk about is having these stack traces in context. So this is a trace from an actual production system that I work on. And you can see that the top level response for this endpoint was successful, but it had this failure in there, highlighted in red there. So if we click on that, we can see what the stack trace was and what the error was in the Elixir code. But the real power here is that you can click around to all the other traces that led to that failure. You can see like what functions were called and like whatever metadata you chose to include. So you could maybe work out what was the URL that the user originally hit that led to this error, or maybe somewhere intermediately, like what parameters were passed to a function that caused it to fail. Another easy one here is N+1 database queries. This is an example that I made on purpose, so no shame. If we zoom in here, we can see that in the controller, I get a list of user IDs, and then I materialize each of those user IDs, hydrate them into like blog posts that user wrote in a view. And this is something that is fairly common in practice, but when you see it pointed out to you like this with like thousands of database calls instead of one, it becomes pretty obvious when you're looking at the traces. We can see here that the span list has 1,589 spans in it. So that's a lot of database calls compared to one. Another thing to watch out for is calls to the same service. We can see this, for example, in this, there's a sequence of calls that are being done in parallel, and 3 of them end up going to the same service. So maybe there's a way that you could arrange for figuring out which things do you want to get in bulk and then get all 3 of them in one HTTP call, maybe reduce the load on the downstream service, or just get the response back more quickly. On the flip side of that coin, maybe you have opportunities to do things asynchronously instead of making one big call to the downstream service. For example, if you can very quickly get a list of IDs, then you can hydrate those IDs with 2 downstream services instead of waiting for a fully hydrated response and then pulling the IDs out and sending it to another service. It might actually lengthen your overall time. I don't have a picture for that one. Network latency is another neat thing that you can find really easily. So see if you can figure out where the network latency is. We have an external request client here that's making a call to downstream services. So all these gaps in here, I mean, obviously there's a lot of things at play here. It isn't all network latency, but these are some easy things to point out that a lot of that could be network latency because we're making a downstream call, and then we see where the downstream service was doing its work, and there's no accounting for what else was going on during that time. So a lot of it's probably network latency, just waiting for the HTTP request to go and come back. Probably the most important superpower is the culture shift that comes with being able to share links to these traces with your colleagues when you're talking about how the code works, why it's failing, why it's slow. Instead of working with gut feelings and past experience and, oh, I know how this metric works, I'm going to go look at my personal dashboard, whatever, we just share these links to Datadog APM traces, and then we instantly have context of exactly what the person's talking about and what they mean, what they expected, what they didn't see. Along with the superpowers, there's going to be pitfalls. Like everything, there's trade-offs. You need to make sure you think about sampling. If you send every trace that you collect to the backend collector, you might end up paying Datadog a lot of money, for example, or New Relic or whatever vendor you're using. Or if you decide to go the open source route with Jaeger or Zipkin, you might just crash your service and then nobody gets traces anymore. Another important thing to consider is incomplete traces. So like I mentioned with the context propagation through HTTP headers, if you ever fail to do that, then the downstream service won't be connected to the upstream service in your trace. So you'll just have no visibility there. And potentially worse, if the downstream services are tracing, but they don't have the context, then they'll just have a separate trace from there on down. And that can be really confusing and hard to find what really happened. Another kind of weird thing that you wouldn't think about until you start looking at it is clock skew. So even if all of your servers are using NTP to set their clocks on the kinds of timescales we're talking about, there's a good chance that there's some clock skew. This is a real thing from a real trace where we have a downstream call getting made, and the downstream service was kind enough to predict that we were going to call it ahead of time, and it just started working ahead of time and saved us a few milliseconds. So that was great. I don't know why there's a whole bunch of network latency at the end. Yeah, no, I'm kidding. Like, it actually started way in the middle there, but like the clocks are off a little bit. Okay, so I want to talk quickly about a couple of standards or non-standards, as the case may be, with OpenCensus and OpenTracing. OpenTracing is a cloud-native computing foundation project, and they have first-class support for several different languages, not including Elixir or Erlang. But on their website, if you go look, OpenTracing is not something you can download, and it's not a standard. So it's an API spec, and it's various implementations. So the way that I read that is that practitioners needed something, and they built something, and they decided kind of like, this is how we're going to use this thing. And some examples are the Spandex project that I work on for Elixir. There's also Otter for Erlang, and X-Ray is kind of a wrapper around Otter using Elixir, and various others. There's also some vendor support. I mean, I guess open source as a vendor, but Nginx, for example, allows you to export traces using OpenTracing for requests that go through their proxy, which I think is amazing, and I didn't expect that to be a thing. But now that it's a thing, I want all services to have this kind of thing where, like, if you make a request into some database, I want to see what the database was doing. Or if you're passing through a proxy, I want to see, like, what were you doing in there before you passed on the request to something else. How long was it queuing in Nginx, for example? So the other big standard is OpenCensus. On kind of the opposite of OpenTracing, it is a single set of libraries. There's an official set of libraries for it. And in addition to traces, it also handles metrics. And the plan is for it to also handle logs as like a standard observability platform. This is just a quick graph of how you can deploy OpenCensus. You'll note that there is no such graph for OpenTracing because it's kind of like up to you or up to your vendor or whatever to have your code talk directly to a vendor, whereas OpenCensus is explicitly vendor agnostic. There's a bunch of different deployment options for whether you're deploying in a container or on a dedicated host, or if you just want your library to directly export to an OpenCensus collector. And also, this is where we get our tail-based sampling. So for example, if you're sending traces to Datadog APM directly, you don't have any direct control over tail sampling. It's kind of up to them to sample it however they want to, based on rate limiting or probability or whatever. But in OpenCensus, we have the ability to do tail-based sampling because we control the OpenCensus collector. We can configure it ourselves. Another important thing here is that you can output each collector to multiple destinations like open source solutions, Jaeger, Zipkin, Prometheus, but also to another collector and also to various vendor backends. And what that allows you to do is, for example, you can filter down certain spans to go to your open source Zipkin that you run internally and maybe not rate limit those quite as much. And then for your vendor solution, you send only errors or only long traces or whatever you want to do. And then you end up maybe paying less and still getting the same value. The really good news, though, is that OpenTracing and OpenCensus are merging together into a thing called Open Telemetry. So it's like the first example of a win on standardization causing less standards. The timeline for the merger is this year, starting the official project launch next week. So that's great news. They're really moving quickly on it. This is the Spandex project that Zach Daniel and I maintain. It has some easy integrations with Phoenix and Plug and Ecto. On the downside, it's really only Elixir. It has a lot of Elixir macros that would be really tedious to try to use from Erlang. It implements the OpenTracing standard, which is kind of less going to make it into Open Telemetry than the OpenCensus standard. And it also only supports Datadog APM currently. So the plan is that we're going to work with the OpenCensus team, which currently supports Erlang and Elixir both very well, implements the OpenCensus standard, and has various trace collectors, including Datadog APM, so super set of features. And the plan is to have these teams kind of combine together into whatever turns out to be the thing with Open Telemetry to be determined. Okay, so I want to quickly talk about the features in the Beam that we can use other than these built-in functions. And to do that, I want to talk using the Spandex example project that I set up to help people use Spandex. Again, this doesn't use Erlang trace, so we'll talk about some things that it does use and some things that it could maybe use in the future. We already looked at an actual Datadog trace of it, but this is kind of the schematic overview of how it works. We have HTTP clients that are calling into a plug gateway, talking to a Phoenix backend, and then there's an Ecto repo that we model as a separate service, even though it's kind of part of the Phoenix backend. So then we get traces that look roughly like this. And the way that we get those is in your Phoenix backend, well, actually in both services, you'll end up having a worker here that knows how to send traces to Datadog. And then you can configure that using whatever configuration methods you prefer, whether it's environment variables or mixed config or just falling back to a default. And then this is all you have to do in your Phoenix endpoint to get top-level spans out of Phoenix. We have a wrapper that kind of wraps around your plug endpoint and catches stack traces and reports the start and end time. We also have function decorators that you can put into whatever module you want to. You just use Spandex decorators and then decorate span. And then we plug into Phoenix instrumenters if you're not using telemetry yet. And we have Ecto logger instrumentation as well. One quick note here is that if you're using something like plug error handler, you might want to make sure you put it before Spandex so that you get logs of errors and crashes and stuff before the error handler handles them, because then you won't see them because it doesn't necessarily re-raise them. And then this is an example of how the context propagation works. Spandex library has an inject context function that you can use to inject the tracing headers into a list of headers that you're going to pass to HTTP Poison or Mint or whatever HTTP client you're using. And then this is kind of a look behind the curtain of how Spandex actually works. We just use Elixir macros to do a little bit of setup and then just unquote the body. So basically call the body of the macro. But we wrap it in a try and a rescue so that we can capture any errors and send them up as a span, and then make sure we finish the span afterwards, whether it crashed or not. An important thing there is that there's a re-raise exception stack trace in there so that Spandex itself isn't eating all of your errors. It's transparently re-raising them for you, so then you can handle them elsewhere. Okay, so features to trace across Beam processes. The main thing that Spandex uses, and probably other libraries are going to use, is the process dictionary. We often train newbies not to use process dictionary because it's mutable state, but in this case it makes a lot of sense, similar to how logger metadata works, where you don't have to have your user code passing around a trace context from one function to the next all the time. You can just call start trace and start span and finish trace and finish span, and it just knows how to keep track of what the current span stack is in the process dictionary. So that it can push and pop new spans onto the stack. This is something we're not using yet, but I'm excited to potentially use in the future. With Elixir 1.8, we get this callers thing in the process dictionary. And what that does is when you spawn a task, you can tell from the task process, you can tell where it was called from, and then potentially look up in ETS or somewhere else what the trace ID and span ID were at that time. So that you can do a little bit of magic for people. They don't have to pass the trace context manually. Because if you did need to pass it manually, this is how you would need to do it, is ask what the current context is, and then use the fact that this anonymous function is a closure. You can pass in the tracing context inside the task, which kind of passes it across the process boundary. But that's a mess, and you shouldn't have to do that. So we want to make it easier. Another thing we don't use that would be interesting is the seek trace function, where you can set a tracing ID in a parent process, and then any messages or gen server calls or whatever that happen will automatically and transparently pass that to the child process, so that in the child process you can continue that span if you need to. Again, this doesn't use Erlang trace. All right, so I'm out of time. I just wanted to mention really quickly that if all of that was too complicated for you and you're a library author and you don't want to integrate OpenCensus, telemetry is another thing to look into. It's super simple and it's relatively standard and relatively safe. So you can basically, your library can execute a telemetry event and a receiver can attach to it, and then they can handle that however they want to. And I'll skip past a lot of this stuff because I'm just out of time. But the takeaways are you should trace your app, you should trace your libraries, and look into open telemetry and regular telemetry as the case may be. Thank you.